Hearing the word relativity may make you think of Albert Einstein. That's one of the things he's most famous for, is his understanding of special relativity in this equation E equals mc squared. Special relativity refers to things that are moving close to or at the speed of light. But relativity is actually an old concept. It's well before Albert Einstein. It's attributed to Galileo in the 1500s, but it was probably used and established before then. But he was one of the sort of the founders of what is known as classical mechanics. And so relativity was something he talked about, in that if you're moving at a constant velocity, you can describe motion accurately, and it doesn't matter what your frame of reference is. The things you need to know for AP Physics 1 is that when we're talking about relative motion, we're talking about things that are moving at a constant velocity. So you can either be moving forwards, backwards, or not moving. That is a case of constant velocity. It's often referred to as being stationary or at rest in AP Physics 1. But it's the idea that if you're observing motion and you're moving at a constant velocity, then all the equations that we use in your descriptions will all be valid. This can sometimes be referred to as an inertial reference frame. Inertial reference frame means that your perspective is moving at a constant velocity, whether you're on a boat or a train or walking or standing. As long as you're not speeding up or slowing down or changing direction, then these ideas apply. The general relationship that'll be useful for AP Physics 1 is this idea that from your perspective as an observer, you can figure out these relative motions if you add up the velocities of the things that you're observing. And this is going to be important in considering positive and negative directions. We've talked about positive and negative directions for a while, so it's important that you declare those, because that will make the relative motion come out accurately when you're trying to calculate it or describe it. I've assigned you some questions from AP Classroom. This is a student view, so I can kind of have your perspective on this. There's two good videos that give you an introduction to what relative motion is. It can be confusing because you've spent your entire life looking at the world from your own perspective or your own frame of reference, and this introduces how you look at the world from different frames of reference. You're going to do the quiz online through AP Classroom. I have set it up so that you can check your work as you go through. So I just want to make sure everyone's clear on how this works. And so what you can do is you can read through the question, try it yourself, and then check it out, click the choice, and then before going to next, do check answer. If it highlights in red, that means the answer is incorrect, and if you scroll down, it will give you a very brief explanation as to why it's incorrect. So try it again, and then once you pick the right answer, it'll be highlighted in green, and it'll emphasize the correct answer. Don't move on to the next question until you've checked your answer, or at least don't submit. That's the most important thing. Don't submit the entire quiz until you've checked your work. AP Classroom doesn't let you resubmit. My hope is that you'd be able to resubmit and do this as many times, but you have to check your work and then get the right answer. That's the only way you can change your answer. Once you submit, then it's locked in. Because my hope is that you get all these questions correct, and I give you full credit for that. The AP Classroom videos offer a nice general approach to solving relative motion, and I want to help you get started on some of these questions just to get your wheels turning here, and then you can check your answers on AP Classroom and get the correct answer before you submit. So this first problem here, water flows in a river uniformly to the east with a speed of 5 meters per second relative to the shore. A boat traveling west at 10 meters per second relative to the water. Passengers on the boat walking at 5 meters per second to the east towards the back of the boat. Which of the following statements about the passenger's velocity is correct and gives the correct reason? All right, there's a lot going on here. So the best thing to always do is to try and draw out what's happening. So we have a river, and it's flowing to the east. I'll make east to the right and west to the left. Okay, so it seems like the river's flowing this way. So I'm going to call this V river, 5 meters per second. Then there's a boat. It doesn't have to be a beautiful boat. traveling west at 10 meters per second relative to the water. Okay, so there's the velocity of boat, 10 meters per second. And then there's a passenger walking 5 meters per second to the east toward the back of the boat. So there's the person, I'll call him V-pass or passenger, 5 meters per second. And we're trying to figure out what about the statement is about the passenger's velocity is correct, and we're talking all these choices give an answer relative to the shore, so we're considering you as an observer on the shore. Okay. With all these velocities, and especially going in opposite directions, it's important to consider what's positive and what's negative direction. So I'm just going to say east is positive and west is negative. And then the relationship you want to consider is that the perspective of velocity from an observer, you on the shore, is the sum of all the velocities that are in play here. So we have the velocity of the river, the velocity of the boat itself, and then the velocity of the person on the boat, the passenger. Okay? And so if you put in these velocities while also considering that going to the west is the negative direction and going to the east is the positive direction, you'll get a final answer here that should match up with one of these four choices. For question 2, we have a student riding on a bus that's traveling east. The student walks towards the front of the bus, and an observer who's stationary is outside the bus claims that the student is moving faster than the bus. Is this claim correct? Why or why not? Once again, with all these motions, it's important to draw out what's going on. Okay, west and east. I'll say east is positive, west is negative again. And so we have the bus, velocity of bus, there's no number given here. And then there's the velocity of a person walking towards the front. So the bus is traveling to the east, we're assuming the person is also going to, the student here is going to travel to the east. Okay. And so if you consider what's going on here, we have the velocity of you, the observer, standing on the outside. You'll consider all the velocities with the velocity of the student and the velocity of the bus. There's no numbers here, but this idea should match up with one of those choices. Number 3 tries to throw a little bit of a curve in here by talking about something that's accelerating. And this can be tricky because acceleration may or may not involve relative motion. It depends on whether or not the observer is accelerating. So we have a rowboat moving in a lake accelerating at a constant rate towards the shore. The observer in another boat is moving at a constant velocity. Okay, so we have one observer, constant velocity, so this is okay. Measures the rowboat's acceleration. A second observer is standing still. That's also constant velocity. So these two observers are okay if we're trying to consider relative motion here. Also measures the acceleration of the rowboat. Are the two accelerations measured by the two observers the same? Why or why not? Okay, they're observing something that's accelerating, but as long as the observers are at constant velocity, okay, which can either be moving or not moving, zero velocity, these are sometimes called inertial reference frames. Okay. So as long as your reference frames are inertial, or that your observers are moving at a constant velocity, then relative motion can be considered. We have a plane here flying, and it has some speed relative to the ground, so there's going to be some sort of observer on the ground, most likely you, the person in the problem. While in flight, the plane ejects exhaust in the opposite direction of speed of VEP relative to the plane, which correction directly represents the velocity of the exhaust relative to the ground. That's going to be the observer's perspective, and similar to a previous couple problems, looks like the plane's traveling to the right here, which we'll say is east. West is negative. And so if we're trying to consider what the observer sees about this exhaust, then you have to consider the two velocities here, the velocity of the plane and the velocity of the exhaust relative to the plane. But note that they're going in opposite directions, so that will affect how you plug in these values here. This next problem is an odd game of darts where one time the dart is just being launched from rest and the other one it's in something that's moving and then it gets launched. We have a cart equipped with a launcher and it launches the dart horizontally. The dart is always given the same horizontal velocity relative to the cart. In trial 1, the cart is at rest at point P at a distance d from the target and launches the dart forward towards the target. So I'm going to stop there and just analyze motion 1 first. And we're going to try and figure out how fast the dart goes. Well, the velocity of anything is the displacement over the time. So the velocity of the dart is how far it traveled, which is given as d. And we're given that it takes t1 for it to go this distance. So that's the speed of the dart in variables. All right, the second scenario, the cart is moving forward at a velocity of v, their constant speed of v cart, and launches the dart at the instant the cart's at point P. So they're both getting launched at the same spot, and as a result, they're both going to travel the same distance d. The time the dart takes to reach the target is t2. Cart has negligible change in speed, which the following is the correct expression for the speed of the cart. Okay. So the dart is going to look like it's going a little bit faster from the observer on the ground. And so if we consider this relationship, it's going to be the velocity of the dart, because the dart, as it said, is always given the same horizontal velocity. But then it's going to look like it's going a little bit faster because the cart is moving forward. So from the observer's perspective, we're going to try to figure this out. And because the observer looks like it has the dart going at a greater velocity, so the dart's still covering the same distance before, it's just doing it in a shorter time, well, what we're going to assume is a shorter time for time 2. So this is the speed that the observer is going to see the dart moving at. And because it said the dart always has the same speed, so it always seems like it's going to be pushed back by the same amount and come out at the same velocity, this will apply over here. Okay. And we're trying to figure out the velocity of the cart. Okay. So if you go ahead and solve for v cart, that should help you get the correct answer for 5. Question 6 has a lot going on, so we're just going to go right into the drawing as we read this. Train is moving to the east 25 meters per second relative to the ground. So there's my train. It's going east at 25 meters per second. There's a person on the back of the train who's going to throw a ball to the west with an initial speed of 15 meters per second relative to the train. What's the initial velocity of the ball relative to the ground? So that's basically considering us, the observer on the outside. We have 2 directions going on here, so you're going to want to consider the opposites with your signs. One direction is going to be positive, one direction is going to be negative. And if you want the velocity from the ground, or the perspective of velocity from the ground, you'll take all the velocities that were in play here and add them up, considering that they're going in opposite directions, and that will get you to the correct choice.